In this section, we're going to learn about binomial probability distributions. This section presents a basic definition of a binomial distribution, along with notation and methods for finding probability values. Binomial probability distributions allow us to deal with circumstances in which the outcomes belong to two relevant categories, such as acceptable and defective, or survived or died. Here's some notation for probability distributions. Capital S and capital F represent a success and failure. These denote the two possible categories of all outcomes. Lowercase p and lowercase q will denote the probabilities of a success or a failure. So, P of S is equal to P, where lowercase p is the probability of a success. And then to find the probability of a failure, that would be denoted by lowercase q. So if we know that P is a 60% probability, Q would be a 40% probability because their sum is 100%. In decimal form, you would subtract from 1. Here are the requirements of a binomial probability distribution. First, the procedure has to have a fixed number of trials. The trials must be independent. That means that the outcomes of any individual trial cannot affect the probabilities in the other trials that occur. Also, each trial must only have two outcomes. These outcomes are classified as a success and failure. The probability of a success remains the same in all trials. Here's some more notation. N represents the number of trials. X is the number of successes that we want in n trials. P is the probability of a success in any one of the trials. Q is the probability of a failure in any one of the trials. And capital P of X is the probability of getting exactly X successes in n trials. Be sure that X and P both refer to the same category being called a success. When sampling without replacement, we can consider events to be independent if n, our total trials, is smaller than 0.05 of capital N. So this means that 5%, we have to have our sample must be smaller than 5% of the population. If that occurs, then we can actually look at the events as being independent. When an adult is randomly selected, there is a 0.85 probability that this person knows what Twitter is. So suppose we want to find the probability that exactly 3 of 5 randomly selected adults know of Twitter. So is this a binomial distribution? Yes. There are 5 trials, and each time we pick a person, their answer doesn't affect the previous person's answer, so they are independent trials. And each trial also has 2 outcomes or 2 answers. They either do know of Twitter or they don't. So there is a constant probability of 0.85 each time that an adult knows of Twitter. Let's determine if the given procedure is a binomial distribution or not. Surveying 12 jurors and recording whether there is a no response when they are asked if they have ever been convicted of a felony. So this would be a binomial distribution because there's only 2 outcomes here, yes or no. Treating 50 smokers with Nicorette and recording whether there is a yes response when they are asked if they experience any mouth or throat soreness. This also is a binomial procedure. So the outcomes are 2 outcomes, either yes or no. Recording the number of children in 250 families. This would not be binomial because there are more than 2 outcomes for this procedure. 15 different governors are randomly selected from the 50 governors currently in office, and the sex of each governor is recorded. So this is not binomial, and here's why. Since we have a sample of 15 governors out of 50 total, we need to check how large of a percentage our sample is. 15 divided by 50 is 0.30. That's 30%. So because this does not satisfy the 5% rule, is classifying it as independent, this does not qualify as a binomial sampling. We have to keep in mind that the governors are selected without replacement, so each governor doesn't really have an equal chance of getting selected if we did this type of procedure. We will now discuss two methods for finding the probabilities corresponding to the random variable x in a binomial distribution. So we can use this method of the binomial probability formula. So this is a formula that you'll need to know. And right here is the one that you'll see. P of x is equal to ncx times p to the x times q to the n minus x. Now this ncx is a combination formula, and the way that you work it out by hand is up here. It's a formula involving factorials. It's not necessary to work it out that way though, because your calculator will have an NCR in it, which is the same thing as NCX. NCR is located where the probability button is on your calculator, or sometimes it might be on the face of your calculator, like above the number 3 you might see NCR. So because that formula is embedded in your calculator, you won't need to use this factorial formula. So the probability of getting x successes is calculated where we do n, which is the total trials, cx, so it's a combination, so n total trials combination x successes at a time. P is the probability of a success, and we raise that to the power of x, and we multiply by q, which is the probability of a failure, and it's the opposite of p. We raise that to the power where we subtract the x from n. So n is the number of trials, x is the number of successes among n trials, p is the probability of success, and q is the probability of failure. There's another way to look up these answers, and it's by using table A1 in the book's appendix. Part of table A1 is shown below. So we can only use table A1 if the probability of success in our problem is actually listed in that table. So at the top of the table you'll see a P, and it's usually going to be something like a 0.70, a 0.80, so something like that. So if we had something like a 0.62 for our P, we could not use table A1, and we must use the binomial formula. But here's how we would read the table. With n equals 12, so let's say that we did 12 trials, and we're told that the probability of a success is 80%, so P is 0.80. The probabilities of 4, 5, 6, and 7 successes are shown. So n is 12, and the probability of getting 4 successes for 12 trials, if the probability of an individual success is 80%, is going to be this, 0.001. Probability of getting 5 successes out of 12 trials is 0.003. So you just have to read going from n to your x to your probability. So we can use table A1 if the given probability is one on the table. So here's some of the probabilities that you'll see on the table. If the given probability is not in table A1, then you must use the binomial formula, which is the ncx times p to the x times q to the n minus x. So for this first example, let's practice using table A1. Find the probability of x successes given the probability p of success on a given trial. So n is 4, so it's 4 trials. X is 3, so we want 3 successes out of 4 trials. And P, the probability of a success, is 0.30. So 0.30 is a probability that's on the heading of table A1, so we can look this up. So looking it up in the table, we should get that the probability when we go N is 4, X would be 0, 1, 2, 3. It always counts up to the top, so you go to X is 3, and then you go under P is 0.30, and then you'll find your answer, 0.076. Next, let's use the binomial formula to find the probability. So N is 6, X is 4, and P is 0.75. So table A1 isn't helpful because it doesn't include this particular probability. So we have to use the probability formula. P of X is NCX times P to the X times Q to the N minus X. So the probability of getting 4 successes is 6C4. So when you set this up, your left side number will always be the larger number. It's always the total. And the lower number, or the number of successes, goes on the right of your C. 0.75 is the P. Raise that to the power of the 4 times 0.25, that's the Q. So we do 1 minus 0.75 to get the 0.25. And we subtract the C number, 6 minus 4, to get the power of the Q. So in your calculator, most of them you're going to start with typing the left side number of your C. So 6, and then you hit your probability button if that's the type of function key that you have. So 6 probability, arrow to NCR, and hit enter. So right now the screen says 6 NCR. So now you're going to finish it, and you're going to type 4 parentheses 0.75 to the 4th parentheses 0.25 to the 6 minus 4. Notice the use of parentheses here for that power. And this is the value that you should get. If your calculator does not have the probability button and it has like the NCR above of number 3 or some other number like that, then you're going to have to hit your second key or your shift key to access NCR. So you would still do the left side number 6, and then you would do second NCR, and then you would hit your right side number 4, and then you would just keep going. You could use parentheses or times. Find the probability that at most 2 subjects experiences headaches. So we're going to use this table here. This table is already set up. It's a binomial probability distribution with N equals 6 trials, and P, probability of a success in an individual trial, is 0.167. So we want to find the probability from this table that at most 2 subjects experiences headaches, and then we want to know if that's unusual. So the probability of at most 2, the phrase at most is always reworded as less than or equal to. So less than or equal to 2 in this table would be including 2 and anything smaller. So this is actually 3 separate probabilities, and it's really the probability of getting a 2 or 1 or no headaches. And or means to add. So when I set this up, I'm actually adding these separate probabilities together. So this is going to be adding the 0.3341, 0.4019, and 0.2014 for an answer of 0.9374, or a 93.74% chance. So an unusual probability is classified as being a number less than or equal to 5%, or 0.05. So since 0.9374 is not smaller than 5%, it would not be unusual for at most 2 subjects to experience headaches in this trial. The Hemingway Financial Company prepares tax returns for individuals. According to the IRS, individuals making $25,000 to $50,000 are audited at a rate of 1%. Now the Hemingway Company prepares 5 tax returns for individuals in that tax bracket, and 3 of them are audited. So this sounds kind of fishy because 3 out of the 5 tax returns in that bracket got audited, and that seems like a much smaller or a much higher rate of audit than the 1% reported by the IRS. So let's do some investigation here. Find the probability that when 5 people making $25,000 to $50,000 are randomly selected, exactly 3 of them are audited. So this is a binomial probability distribution because these trials are supposed to be independent. So when I select one person and then the second person and the third, those are independent selections. And also, they're either getting audited or not, so there's 2 outcomes. So when we understand that it's a binomial probability distribution, we need to understand the notation that goes in the formula. So it's the NCX times P to the X times Q to the N minus X. So you look at this formula and you need to know an N, an X, a P, and a Q. So N is the total trials. So N is going to be 5. P is going to be the probability of success. So what this means for us is the probability of getting audited. Probability of getting audited is 1%, so we make that a decimal and it's 0.01. Now X is 3. So when you look at this, you're going to have 2 numbers, 5 and 3. So 5 is larger, that's going to be the total. 3 is the number that we want to get repetitively audited. The only thing missing is Q. So Q is going to be 1 minus P. It's the opposite of P. So 1 minus 0.01 gives me my Q, which is going to be, let's see, well, that would be 99%, so 0.99. So do I have to use this formula here? Well, if I can look it up in table A1, I will, because that's quicker. And so I just need to see if this probability of 0.01 is listed in table A1. And it is. So I'm going to look these answers up in table A1 instead of using the binomial formula for it. Okay, so when I go to table A1, what I'm doing is I'm going to N, and I go to N is 5. And then when you look at your X's, it's going to be 0, 1, 2, 3, 4, or 5. So we want to find exactly one X. So X is 3. So we go to 5, we go to 3, and then we want to look at our P. So for the P, it's 0.01. And so the answer there is 0 plus. So it's a very, very small probability when it says 0 plus. It's a positive probability, but it's just a very small probability. Okay, so now let's go ahead and look at another kind of question here. So we found that the probability that if we randomly select 3 people, they get audited, that was almost a 0% chance. Now let's find the probability that at least 3 people are audited. So here, N is 5 and P is still 0.01. But when I put at least in it, that's indicating more than 3. So at least 3 is 3 or 4 or 5, because you can't go more than the total. Or means add. So this is the probability of 3 people audited plus the probability of 4 people audited plus the probability of 5 people audited. So watch out for phrases like at least or at most, because you're going to have to separate it into the individual probabilities and you're going to have to add them. And you have to look up these separate answers. And so I'm going to still look up in table A3. And I'm going to look up the probability of 3 people. And I remember that was a 0 plus. So X is 3. So you actually have more than one X. You have X is 3, X is 4, X is 5. So probability of 4, 0 plus again. Probability of 5, 0 plus again. So the probability of having at least 3 people audited is 0. So based on those results, what's our conclusion? Are they unlucky, or are they being targeted? So we found that the probability of the IRS randomly selecting 3 of 5 tax returns for audit It's so low, almost zero, so we can assume that the individuals were being targeted for audits and that it's not occurring by chance.